Thank you very much for the introduction. So, hello everybody. My name is Hakim Si-Mohammed and I am from INRIA, France. My PhD is about brain-computer interfaces and augmented reality. And today I'm going to present you some of the results we got regarding the combination of these two technologies together. But, well, I suppose most of you are familiar with AR, so I will give you first a quick overview of what is a BCI. So basically, a brain-computer interface is a system that acquires brain activity, usually under the form of electroencephalography, EEG, and then translates it into a command for a computer or any other device. And one type of brain activity that we use for interaction is called the SSVEP. So basically, it is based on the fact that when a subject is focusing on a flickering light at a certain frequency, the brain responds with an activity with an increase of its activity at the same frequency of the simulation. So if we want to use that for interact, usually we display several flickering targets at different frequencies that we are able to detect to understand what command the user wants to say. So if you take the man shooter here, the example, so you have the different wings flickering at different frequencies plus the cannon. And then you can, if the user focuses on here, it goes right. If the user focuses here, left, and here for firing. Okay, so remember this concept because we're going to use it for the rest of the presentation. So, and combining BCIs with augmented reality is really interesting for many different application domains. And I'm not going to go through the state of the art here. If you're interested, you can go to and see a paper that we've already written on the subject. But what is important to remember is that no one yet has tried to combine BCIs with optical see-through augmented reality devices, and that nobody yet systematically studied all the underlying effects of combining BCIs and ARs in terms of compatibility and user designs. So these are the questions that we want to answer in this research. So first, just the very compatibility of the two headsets together. So is it possible to use a BCI and an AR HMD at the same time? And then how do we design user interfaces that are at the same time intuitive for the users and efficient in terms of BCI. Quick notes, I will use the terms, here I speak about BCI to speak about SSVEP, remember? And when I will use the term BCI performance or SSVP performance, I mean the classification accuracy. And when I just say targets, I mean the flickering targets for the commands. Well, for answering these questions, we've designed 4 user studies that I'm going to go through. The first one was about testing the electrical and the physical compatibility of the BCI with the AR headset that was a Microsoft HoloLens. So we designed an experiment with 4 conditions. We first had a control condition where the targets were just displayed on the TV screen and the users had to perform a series of SSVP selections. Then we just put the HoloLens on top of the BCI without turning it on, just to see if the physical presence of the HoloLens would disturb the signal. Later, we displayed still the targets on the TV screen, but we turned on the HoloLens just to see if the electrical activity of the headset would disturb the signal. And last condition, we displayed everything on HoloLens. And always, the task was to make a series of SSVP selections. Interestingly, the results showed that there was no significant decrease of performance or no significant difference of performance regarding all the conditions, around 80%, which represent the state of the art somehow. And the result was that, okay, yeah, apparently it is possible to use a OST HMD with an SSVP BCI at the same time. But one of the interests of having an AR device HMD is that we are able to move while interacting. But we know that movement and martial activity usually decrease BCI performance. So we decided to conduct an experiment to see what was the effect of head movement on that. So in this experiment, we have always a control condition with SSVP performance, SSVP selections without any movement, then with low movement amplitude, something like that. And then we had 80 degrees and 160 degrees, so really going to 80 to the right and 80 degrees to the left. And we conducted the tests. And in line with our hypothesis, we saw a clear decrease of performance with the augmentation of the amplitude of movement. But interestingly, the BCI seemed to tolerate a small amplitude head movement, something like not very fast and not very, like 40 degrees, 20 to the left, 20 to the right, and no, not very fast. And then when we had these results about the possibility to use the BCI with the OST HMD, the question was, how do we characterize the design space of, or how do we use the augmented reality, how do we display the user interface on it? So we decided to take the case of a robot control application to illustrate the prototype. So this robot had three possible commands: going forward, rotate to the left, and rotate to the right, associated with three targets. So one target would put it to the front, forward, left, and right. And we identified that the different possibilities to display the targets in such an application case was characterized by 5 dimensions that I'm going to go through. The first one was the orientation of the targets. We could either have frontally oriented target or transversally oriented target, like the plane containing the targets could be parallel to the plane of movement or parallel to the user field of view. Then we had the frame of reference, where the target could be exocentered or ego-centered, meaning that the rotation of the robot would imply the rotation of the targets, or they would be always fixated to the user. Then we had the anchorage, whether we would fixate the targets to the robot or always to the center of the field of view of the user. Then the size, whether we would make the targets bigger if the robots go further to always have the same size, or if the robot go further, then the targets would appear smaller. And lastly, the explicitness, whether it would be a direct link or explicit association between each target and the direction it leads the robot to. Like here, we know that this puts it to the forward, left, and right. And this is just for occlusion that we did not display the link. So for evaluating all these, by combining these 5 dimensions of 2 modalities, we ended up with 32 different display strategies that we wanted to evaluate from the user. So here what the strategies give. So you have the 32 different possible displays, and you can see that some of them are really different from others. If you take this one, DS29, it is somehow very different from another one, like in here, where the targets are frontal, where here they're transversal. Okay, so there are all the combinations here. The experiment was conducted on 42 participants in an online questionnaire, where they had to rate the videos on a 7-level Likert scale. Then we performed a majority voting test to identify or to evaluate how the videos were perceived. The results of the study showed that 2 dimensions were really the most prominent in terms of perception of the user or intuitiveness of the display strategy. We identified clearly 4 groups with significant difference between each other. We could clusterize videos in 4 groups, and it was depending on the 2 dimensions, which are orientation and frame of reference. So now that we know that user usually preferred exocentered and transversally oriented displays, we wanted to know if what was the effect of the display strategy on the BCI performance. Because, of course, it is good to have a very intuitive display strategy, but we also want to have a BCI that is well-performing. We decided to select the best performing video of each of the 4 groups. So these are the groups that were clusterized, and we took the best performing of each one of them. And then we decided to test these display strategies in terms of BCI performance. We conducted an experiment where the users had to perform a series of SSVP selections, taking the robot from an origin to a destination there. And you can see here that the targets are transversal and exocentered. So here to go forward, to go left, to go right. So this is faster. Here the targets are frontal. And yeah, so the users had to focus every time on one of the targets to take the robot to the destination. And then we evaluated the performance at the end. The results were that, yes, the display strategy had an effect on the SSVP performance of the subjects, but interestingly, there didn't seem to be a significant difference between DS0 and DS29, meaning that, okay, we can at the same time have a intuitive display strategy without losing too much of BCI performance. And we decided at the end to illustrate the global results, the overall results, on a prototype of a robot control prototype, a real robot control. Here was the architecture. So basically the brain activity was acquired and processed through OpenVibe that would send the results to a VISP-controlled robot and to the HoloLens. Here's a video of the last prototype. So here you can have a first-person view of what the user was seeing, and the task was to go from the 4 different points. And it worked pretty well, displaying the real potential and the real possibility to have a real use case scenario using an AR headset with a BCI. To summarize, we conducted 4 experiments. The first one showed the compatibility of the 2 devices together, electrically and physically. Then we showed that, okay, head movements had an effect, but we could still have low amplitude, low speed movements, something really reasonable. We identified the display strategies, finding that the users preferred exocentered and transversal display strategies, and we saw that, okay, the intuitive, the most or the preferred display strategy did not deteriorate the SSVP performance. And lastly, we presented the prototype that was trying to combine everything. So thank you for your attention, and if you have questions, I'll be glad to answer, and you can come discuss every time you want. Thank you.
We have time for questions. Please come to the microphone.
Thanks for the talk. I just wanted to know why you use SSVP, because we always say there is no need. I mean, gaze is always comparable with SSVP. You don't really need a BCI when you can detect the gaze, because SSVP really depends on the gaze. And yeah, that's the first question.
Okay, so thank you for your question. That's really something that comes up often on the comparison. But so there are mainly 2 reasons. The first one is that in terms of BCI, the literature shows that the highest ITR, information transfer rate, is obtained by SSVP. We can say that it is very fast compared to other BCIs. And the fact that it requires little to no training. Okay? And compared to the gaze tracking, in theory, you're right about the fact that it is directed by the gaze, but in theory, what makes SSVP really interesting is the fact that it's modulated by the user attention. So instead of just putting a dwell time, where the problem with gaze trackers is the Midas touch. So if you look at something, then you look at something. So if you just want to gaze without selecting, you cannot do that with a gaze tracker because your eyes are there. But with SSVP, in theory, if you put your eyes somewhere without the intention of focusing on that, you will not give that command. So I'm not sure if I'm really clear on that.
But you have only three targets. So
yes. So for this application case, we have a control robot, but targets go up to 26, and the number of targets can be really increased. We really stayed on 3 targets scenario because the robot could go to 3 directions, but SSVP works also with more targets. I can send you some links about papers going up to 40 targets.
Yeah, thank you very much.
Thank you.
Hi, really great work.
Thank you.
So the performance drop with increased head motion seems like a really big limitation here, because when you want to do this, imagine doing this in AR, you kind of want to have a full range of head motion. Do you have any ideas for how you can mitigate that in future work?
Yeah, so thank you again for the question. Indeed, that's a challenge, but I see in that challenge an opportunity because that means that there's still work to do. And there are works on artifact removal. So these are the performance obtained without any artifact removal done, just trying to filtrate the signal around the frequency of interest. But yeah, the idea would be to try to detect the artifacts that are generated from the head motion, try to delete them. So it is a signal processing challenge that I think can be overtaken. Yes.
Okay. Thank you.
Thank you very much.
All right. Let's thank our speaker.
Thank you.